All right, so today it's going to be composite, exponential, and logarithmic functions, but we're going to be starting with a couple review questions. That's the first one I asked you to work on. Tell me where you started. Plug in the numbers. Before you can plug it in, what do you have to write down? Let's write down the quadratic formula first. What is it?
X equals negative b plus or minus square root squared minus 4 ac over 2a.
Yep. Make sure when you do it, it's all over 2a. I've seen a lot of people mistakenly only have it underneath the square root, but it's underneath everything there. So there's the whole formula. And then you said you plugged in the numbers.
So it would be x equals
Negative 12.
plus or minus the square root 12 squared minus 4 times 2 times negative 46. And then over 2 times 2.
All over 2 times 2. There we go. And then it's a matter of simplifying. Negative 12 plus or minus. So inside here, we're going to have 144 plus what number? 46 times 2 times 4.
I ended up with minus 368.
Yeah, so what happened was if you end up with a negative, it's because it's minus in the formula, minus. And oftentimes, because that's a negative 46, we forget that it's a negative times a negative, which is positive. So it'll be 144 plus whatever that is. What is 46 times 2 times 4? 368. All over 4. Negative 12 plus or minus the square root of, and what's that number? 512. All over 4. Square root of 512. Do we know a number that we know the square? Again, what numbers, when we're doing simplified radical form, we're thinking of all the numbers that I know square roots of. I know the square root of 4, 9, 16, 25, 36, 49, 64. All right. Our instinct usually is to start with the small numbers, but if you can get a bigger one knocked out of the way, it's going to be way faster. So does 64 go into 512? Well, and first off, I know it's not going to be 25 because it doesn't end in 0, or it doesn't end in 25. 25, 75, 50, it doesn't end in those. If you look at these digits, 5 plus 1 is 6, plus 2 is 8. I don't know if you remember all the divisibility rules. If the numbers that I add together are divisible by 3, then 3 goes into it, which would mean 9 might. 5 plus 1 is 6, plus 2 is 8. 8 is not divisible by 3, which means 9 will also not work. I don't know if you've ever been taught those divisibility rules. You know, usually we get stuck with, well, is it even? Yes, it's even, so let's try 4. Let's try a larger even number, 64. Does 64 go into 512? That's someone with a calculator is doing that for me quick. 512 divided by 64. 8 times 64 and 8. The nice thing here is 64 equals 8. The square root of 64 is 8. And then I can go, oh, all right. 8, do I know a number that goes into 8 that I know the square root of? Yep, looking up here, 4 goes in there. That's one of my numbers. 4. 4 times 2 is 8. And I know the square root of 4 is 2. And then when I get to a prime number, a number that cannot be divided by any other number, that little leg of the branch of the tree is done. So I'm left with the square root of 512 is equal to 8 times 2 times the square root of 2. And that's these values here. 8 times 2 times the square root of 2, which is 16 square root of 2. X equals negative 12 plus or minus 16 root 2 all over 4. Which at that point, we're like 97% done. The last thing is to look and see, can we reduce that fraction? A couple different ways you can think about it. I oftentimes think about it like this, negative 12 over 4. So I'm splitting it up. Instead of simplifying, now I'm actually separating it out. 16 root 2 over 4. So that way I can see, can those fractions reduce? Some people are really good at seeing it up front and say, oh yeah, they're all divisible by 4. But if you don't see it, oftentimes this is easier because negative 12 divided by 4 is negative 3. Plus or minus. Here, 16 and 4 reduce. 4 square root of 2. Those are my two answers. Negative 3 plus 4 square root of 2. Negative 3 minus 4 square root of 2. And I'm not, sometimes when you have big numbers like this, you could also take a look at this original equation up here and notice that all of them are even. So I could factor a 2. So 2 parenthesis a squared plus, that's a squared, 6a minus 23. And then I could use these values here. This number would be 1, this is 6, this is negative 23, oh, that's a 6, negative 23 for my a, b, and c, so that they're smaller numbers in the quadratic formula. You would get the same answer. All right, so if you notice that they're all divisible by the same value, can be factored out, factor it out, giving you what's left, and then these are just easier numbers to work with. Do you have to? No. You have access to a calculator on the exam and every place else in life, pretty much, unless you're trapped inside of a, I don't know, someplace where you don't have, you just wouldn't have access to your cell phone anymore. Like, I don't know where that even is anymore, where you wouldn't have a calculator. So, give that one a try. And if you can't remember how, pull out your notes, look at that for steps for completing the square. If you're now realizing that you don't take notes, this is where, at least during studying, you can go, how do you complete the square, Google? And it usually will show you a step-by-step process. It might be slightly different than how I teach it, but it would still get you there. Remembering, of course, you can't use that on the exam because you won't have access to your phones on the exam. As you kind of keep working / finishing up on this, completing the square was also a topic that we hit on very frequently at the last lecture when we talked about finding the vertex form of a parabola. So while we learned it for solving earlier, now we're going to also be using it for finding the vertex form. So we'll do it for solving it now, but then we'll also use it for the vertex form as we complete this problem. First step for completing the square is move constant. So what do I mean? I mean move this constant to the other side of the equation. Subtract 48 from both sides. Plus 32t. That's step 1. Step 2 is to make the a term 1. I need this term to be a 1. How do we do that? Divide everything by negative 16. This will be 3, keeping track of your negatives. Negative divided by negative is a negative, equals t squared minus 2t. Step 3 over here is add half of b and square it to both sides. So that's b, half of negative 2, and square it. So I'm adding half of negative 2 is negative 1. Adding that to both sides. I intentionally left it inside the parentheses on the right side because this number is the complete square. What do I mean by that? This will factor to t minus 1 squared. On the left, I'll actually square it. 1 squared is 1. 1 plus 3 is 4. Now I'm solving for t, which is inside the parentheses. Need to eliminate the parentheses by doing the inverse operation. Inverse of squaring, square root, plus or minus 2 equals t minus 1. To solve for t, add 1 to both sides. 1 plus or minus 2. So t will either equal 1 plus 2, which is 3, or 1 minus 2, which is negative 1. All right. I said vertex form when we did this the other day. Up here, instead of 0, it would have been y equals. So then all along here, I'd have y minus 48. Y plus all that. Y plus this. Y plus or minus 2. But we wouldn't have ended there. We would have actually ended here. So the equation would have been y plus 2, y plus 4 equals t minus 1 squared. If this were in terms of graphing, it would have been y plus 4 equals x minus 1 squared. So all we're doing is looking at that t differently now. It would be possibly an x. In vertex form, this would mean that, again, I'm asking what makes this 0? 1. What makes this 0 on this side? Negative 4. The vertex for that parabola would be at 1 comma negative 4. And then this information down here, this would actually tell me where it intersects the x-axis. So when I'm graphing, I can mark the vertex, I can mark these 2 points on the x-axis, and then I would be making a parabola that would curve up from this point. Try to make this somewhat neat. At 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4. 1, 2, 3, negative 4. The vertex 1 comma negative 4 is over, I meant to have my other tool, over 1 and down 4. 1 comma negative 4, that's the vertex. 3 and negative 1 are the x-intercepts, so I go here to 1, 2, 3. Put a dot. The other intercept is at negative 1. And then it would be a rough sketch, not a V, it's curving at the bottom, a parabola that would look about like that. So completing the square is a very, very valuable tool for finding 1, the vertex, and then 2, the zeros. All right, another quick review question. Boyle's law states that the temperature stays the same, pressure of a gas is inversely proportional. I think this was on the second exam. Or something very similar, probably not the numbers, but the concept is the same. Inversely related, inversely proportional. The generic form is y equals k over x. In this case, it's P in pressure and volume, so pressure is equal to k over volume. Or you could do volume equals k over pressure. Either way, if they're inversely proportional, it doesn't matter which one's which, as long as one's in the numerator, the other one's in the denominator. So if I use this one, inversely proportional, it says when the volume is 1.4, the pressure is 960 kilopascals, and this is an unknown value K. Again, just taking it up here. When the pressure was 960, the volume is 1.4. So I plug those in the inversely formula. This is where you have your calculators out. Got to solve for K, so I got to multiply both sides by 960. K equals 1.4 times 960, which is 1344. So that's my constant. So when it says find the constant of variation, that's it right there. Then I have to rewrite the inverse variation equation. So the inverse variation equation will be volume equals 1344 over P. All right, so that's the equation for whatever V and P. And then it says, third step, find the pressure when the volume increases to 2.5. I'm going to use this equation. It says the volume increases to 2.5. That equals 1344 over P. To solve for P, a couple different ways you could do that. Whenever I have fractions that are equal, I often just say, put it over 1 and use the old school cross multiply technique. .5 times P is 2.5P. 1 times 1,344 is 1344. Then divide by 2.5. And pressure will be whatever that number equals. Which you all have calculators, so I'm assuming you can do. 537.6 kilo pascals. All right, now we're going to get into a little bit of the newer information as we get into functions. We'll be using function notation. Again, function notation just means instead of having y equals 2x plus 1, I'm going to have two different equations. And instead of calling this y1 and y2, I'll call it f of x and g of x. So in this case, we're just going to start with this. take a moment and see if you can just do this quickly. Find f of x plus g of x. Go ahead and do that in your notes. What is f of x plus g of x equal? 3x plus 4. Because what we were doing is just taking these two equations and adding them up. X minus 3 plus 2x plus 7. 3x plus 4. F of 3 plus g of 3. F of 3 means, up here, I take the f of x equation, plug in 3. This 3 goes in there for x. So f of 3 would be 3 minus 3, which is 0. G of 3 is plugging in 3 for the x, so that'd be 2 times 3 minus 7. 6 minus 7 is negative 1.
It would be plus 7.
Plus, oh, it is plus 7, yes, thank you. So those add up to be 1. If I would do 3 in here, I would have oh yes, okay, sorry. 6 plus 7 isn't 1. It's 13. There we go. All right. Plug in 3 for that x. 3 times 3 plus 4. 9 plus 4 is 13. If I find f of x plus g of x, and if I take f of g of the same thing and add them up, they'll be equal to each other because, well, they're equivalent functions. Next step in terms of, and I could have subtracted equations as well. All right, but the next step, these are where we're getting into the concept of what's called a composite function. Composite function. What that means is instead of substituting x in for a value, we're actually substitute an entire function in for a value. So what if we replace the x in f of x, so this f, that x right there, with the entire g of x function. So what I'm going to do is where this x is, I'm replacing it with all of g of x, and we would write that as f of g of x, which means I'm going to take f of 2x plus 7. So wherever the x was for the f of x function, I'm replacing that x with this entire thing. This whole thing goes in here. 2x plus 7 minus 3 will be 2x plus 4. So f of g of x is 2x plus 4. That's what's called a composite function. All right, that's what we just did right there. If I do it the other way around, g of f of x. So now in the x for the g, I'm replacing it with this whole equation. So that x gets replaced in. So we're now looking at this next line down. So instead of 2x plus 7, I have 2 f of x plus 7. This is the f of x equation from up here. This gets plugged in there. And that simplifies to 2x plus 1. Composite functions will oftentimes, in almost all cases, yield different results. F of g of x will be different than g of f of x. All right. Take a moment. With that in mind, see if you can work on this one, f of g of x. And then once you get that answer, if you're confident in what you have, find f of g of 2, which will be taking this equation and just plugging 2 in for x at the end of it. So first, find f of g of x.
For f of g of x, I just wrote out f times x minus 2, and then I did equals 5 times x minus 2 in parentheses.
So this equals what?
So equals 5 times
5 times
x minus 2.
x minus 2. Yeah, so what you started by saying is you said you wrote f times g of x. And just be careful, and that's not what we're talking about, which is a common mistake. So we're not doing, so f of x times g of x is something, but it's not what we're doing. It's not the same as f of g of x. All right, if we're multiplying two functions, that would be 5x times x minus 2. Here we're substituting one in. So the x minus 2 gets plugged into the x equation. So what you have here is correct, yes. Just be careful, we're not saying this, all right? So, not that. So, then we have 5x minus 10, which is f of g of x. F of g of 2 would be then taking that 5x minus 10 and substituting it in substituting in the replacement of the x, replacing it with the number 2. So it'd be 5 times 2 minus 10, which is going to give me 0. 10 minus 10. So if you have all those written down, we're going to do a couple more on the next page. Oh, I included them there. So now what I want to show you is this is how mathematicians tend to abbreviate. It's not really much of an abbreviation. Oh, I even wrote it down there. This means composite function. I know it looks like multiplication a little bit, but it's not. It's an open dot. And we read this f of g of x. So we'd write it f of g of x. So the g of x is going into the f function. The g of x is going into the f of x function. This is g of f of x. So the f of x function goes into the g function. So each of these are identical. F of h of x means h of x is replaced into the f function. It's not a whole lot different in terms of like how many like handwriting things you can write. A lot of things that mathematicians do, we try to do shorthand and like, how can I write fewer things and meaning it say more? This is one of the rare occasions, in my opinion, where this isn't a whole lot different than just writing this. But this is how you're going to see it mathematically more often than this. So what I want you to do is take a moment, find all 4 of those.
Why don't they put like a O in between like the G and X or the F and X?
Over here,
No, on the first one. Because it's G of F of X.
yep, g of f of x. So g of f of x. I'm not understanding the question.
So you said the O.
All right, there we go. David, take a stab at one of them.
I'm gonna try for the next one.
Okay.
I said x minus 2 in parentheses 5.
Is that different than this?
So it's x minus 2 and then in parentheses 5. Because g of x is x minus 2.
G of x is x minus 2. Yep, so g of x is x minus 2.
And you have to put the 5 in.
Where does the 5 go?
In parentheses put 5.
Like this?
No, open
The
parentheses.
5 is in parentheses.
Yeah,
Ah, okay. So the 5 is in parentheses.
yeah.
Where does the 5 in parentheses go?
On the, after the x minus 2.
So like this? Oop,
Yeah,
like that?
yeah.
Okay. And what's your rationale on that?
How did I get it?
Yeah, so like up here, the g of x function is x minus 2. And what was said is that x, so that's g of x, but sorry, it starts with the f of x function. The f function is 5x.
Yes. And the g function is x minus
And in replacement of the x, so instead of 5 times x, it was 5 times the g of x.
Yes.
Because I took all of this, put it in that spot.
Yes.
Now we're doing it the other way around, so g of x is x minus 2. The x, instead of x for g of x, I'm replacing the x with the f of x function.
Would it just be negative 2 times 5x?
What an, oop,
Would it be 5x minus 2?
it would be 5x minus 2, which would be correct. Because this x gets replaced with the f function, that's the f function. So instead of x, it's now 5x. And that is simplified, that's all that can be, so it stays 5x minus 2. Ethan?
So it'd be 5x. And then. Would it just be 5x? Or no, would it be. It wouldn't be 5x. It would be square root of 5x.
All right. What's if you need to, start with what's the f of x function?
5x.
5x. But instead of where the x is, I'm going to replace it with h of x. So instead of 5, again, this here would be times. 5 times x, but now the x isn't x, it's h of x. So it would be 5 times square root of x. And then the last one, the h of x function, there's h of x. I'm going to replace the x with the f of x function. So this replaces, yeah, that's right. So that would be the square root of 5x. When it gets a little bit bigger, usually just means more steps. So f of g of x, the f of x function, this is the one I'm starting with. And the x is going to be replaced with the g of x function. So f of g of x will be 3 times x plus 5 over 3 minus 5. Just took this, replaced it with this function. Threes reduce, x plus 5 minus 5 equals x. That's f of g of x. Try it the other direction. What would you do?
Replace the x with the f with 3x minus 5.
Yep, replace this x
So it'd be
with 3x minus 5s
3x minus 5 plus 5
over 3. Good. Good, good, good. Which will be?
1x.
Oh, careful. Yep. 3x over 3. The plus 5 minus 5 add to 0. The 3 is reduced and it equals x. All right. This is a very unique circumstance. We did f of g of x, g of f of x. Both of them equal x. What that means is that these two functions are what are called inverse functions. An inverse function graphically means if I were to graph this and I were to graph this, they are reflections over the line y equals x. To find inverse functions, what you do is think of it, well, we're going to rewrite them as y equals. So this is y equals 5x. F of x, y equals, right? To find the inverse, I'm going to switch the x and y, then solve for y. So I switch them. So where the y is, I replace it with x. Where the x is, I replace it with y. And then I solve for y. Divide both sides by 5. Y equals x over 5. If I have this equation, I rewrite it as y equals x minus 2. Then I replace the x's with the y's. So instead of y, it's going to be x equals y minus 2. And then solve for y. Add 2 to both sides. Y equals x plus 2. And then the last one over there, h of x equals the square root of x. I'm going to rewrite it as y equals the square root of x. I replace the x for the y. And then solve for y. What's the inverse of square rooting? Squaring. Y equals x squared. All right. The last thing I need to do is I need to actually write the correct, what's the right word for it? Well, let me just do this. We'll do it like this. F to the negative 1x is called the inverse function of f of x, which means down here, this is the inverse of that one. So f inverse of x is x over 5. This one that we did was the inverse of this equation. So that means this will be g to the negative 1 of x equals x plus 2. It's an ugly looking 2. There we go. And then the last one over here, this one, that was the original equation. This was the inverse. That means h negative 1 of x equals x squared. All right, the negative 1 in this case, and down here I don't have it. For some reason my negative 1 didn't show up as it looked like a little hash there, so it's negative 1. The negative 1 on a function does not mean to the negative 1 power. How do I know that? Powers only go on numbers and variables, not on functions. F to the negative 1 of x is this. The inverse of g, and that's how if I read this verbally, this is the inverse function of g. So the inverse function of g to the x, something like that. I don't actually say the negative 1. Inverse function of f of x, that's how I write it. Inverse function of h of x is x squared. And just as a review, what does functions mean? Functions are, if I have one value of x and it maps to one value over here in y, or in this case x2, it's called a function. 2 maps to one thing, 3 maps to d, 4 maps to c. This would be considered a function. 1 maps to b, 2 maps to b, also a function. What would make it not a function is if I have 4 here mapping also to f. The minute 4 both maps to d and 4 maps also to f, this is no longer a function. This is a function. It's called a one-to-one function. One-to-one means each x goes to one y value, and each y value only has one x value. If I erase this back here, this one now does one maps only to one item, 2 maps to one item, 3 maps to one item, 4 maps to one item. This is a function, but b receives both 1 and 2. So this would not be a one-to-one function. This is a function and one-to-one. This is a function not one-to-one. But again, like I said, if I took 4 and mapped it to another one, if that were true, if that had happened, now this is no longer a function. How it looks graphically is like this. If I look at this equation over here and I look at negative 2, so that's my x. When x is negative 2, and I look to the graph, it looks like it's at 3 and at negative 1. So x equals negative 2 maps to 3 and to negative 1. Because I look at the graph at negative 2 for x, there it is. Negative 1 on the graph, positive 3 at the graph. That means this is not a function. If I look at this graph, pick any point on there. If I look at negative 1, there's this 1 point here, it maps to positive 2. If that is true for the whole length of that graph, then this is a function, which it is. All right? So this one, not a function. This one is a function. Do you think this will be a function or not a function, and why? Function or not a function? Function. It is a function. Why is it a function?
Well, if you compare them to the first two, the first one is like a circle,
Mm-hmm.
whatever, and it's closed off, and the other one, it doesn't meet, and so the third one doesn't meet as well.
Okay.
So I kind of just assumed.
So you just assumed. Yep. So again, looking at any point along the x-axis, if I look here at 5, it only touches the graph once, 4, once, going down here, 1, once. At 2, it's only going to hit once. All right, so it's only touching in one place. Function or not a function? function,
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 function.
not a function.
Okay.
Because if I take a point here, like right there for that x, look, I think that's x equals 1/2, or negative 1/2. If I go up, it touches the graph here, and here, and there. There's actually 3 points, 1, 2, 3. In order for it to be a function, it can only touch it once. Function or not a function? Function. Function. Function.
Wait, so then,
To be a function, what we're really going to be talking about, let me do this. It's a procedure called, oh, come on, draw me just a straight line. There we go. It's a procedure called the vertical line test. If I go through this graph here, if it touches more than one place, it's not a function. All right, we go to B. Is it only touching in one place? Even there, it only touches that one spot if we zoomed in. B is a function. I go to C. As it travels past, it only touches it only in one spot. It's a function.
So it only matters vertical, not horizontal.
Right, it only matters vertical. So the vertical line test determines if it's a function or not. All right, passing through there, only touches once. Go up here. Oh, now we're touching twice, 3 times in some places. Not a function. That is a function, that is a function, this is a function. So the vertical line test is how we determine if something's a function or not. Then, there's my horizontal line. If it is a function, so we're only going to look at the ones that are functions. B. Is B a function? Yes, we said it was. The horizontal line test. Does it only touch once? Yes. That means that B is not only a function, it's also a one-to-one function. So again, vertical line test determines whether or not something's a function. Horizontal line test tells me if it's a one-to-one function. Look down here at D. We said D was a function because it only passes through one place all the way along. Take this line, does it touch more than once? Yes. In that case right there, we can see it touches here, 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 here. 4 places. And if we go on, it probably touch a lot more than that. So D is what's considered not a one-to-one function. We look up here at this one. We said A wasn't a function. So it doesn't matter that the horizontal line test works. It can't be if it's not a function, vertical line test, then it can't be a one-to-one function. So if you have a question like, oh, this one's not a function, you cannot then later say, oh, but it's a one-to-one function. The horizontal line test works for letter A up here as one-to-one, but since it doesn't work for vertical, it's not a function. Done. Since it's not a function, it can't be a one-to-one function. It's just not a function. All right, C is a function, not a one-to-one function, because it hits 2 different places. All right, so that's function and not a function. And then also, if it is a function, to know if it's a one-to-one function. All right, we're going to write those down. We're going to graph them on Desmos. If you can't remember Desmos, desmos.com. I'll actually have the app up here on my iPad in a second. So with those, I don't know why that got all moved up on me like that. So when we graphed those, we saw how this is a growth function, that's a decay function. This is a growth function, but it grows negatively. This is a growth function that got shifted a little bit to the right of this one. Decay meant it goes down, and as we talked in good question, because this, no matter how large the x is, it gets bigger and bigger and bigger, so this gets smaller and smaller and smaller, but it will never actually get to zero. When we get out towards infinity, it gets really close to zero, but doesn't actually ever get to zero. So those are the trends we see. When b is a number that's over 1, it grows. When b is a number between 0 and 1, so when b is a fraction, so if b is less than or equal to 1, greater than or equal to, or not greater than or equal to 0, greater than 0, and this should just be less than 1, it's what's called a decay function. When b is greater than 1, it's called a growth function or exponential growth function. And as was mentioned, and as I said, how do I know if it's a exponential function? Exponential functions have x in the exponents. That's how we know it's an exponential function. To solve exponential functions, these are going to be some of the more common ones we're going to be looking at. If I look at 8, I recall that 8 can be rewritten as a number to a power. 8 is equal to 2 times 2 times 2, which is 2 to the third. So if I have 2 to the x equals 2 to the third, x equals 3. When we come back to class on Thursday, we're going to look at how do we do these when they're not these typical numbers. All right. 27 is 3 times 3 times 3. 9 is 3 times 3. So in this one, 9 to the x is 3 squared to the x, and that equals 3 cubed. Powers raised to powers of exponents are rules of exponents. 3 to the 2x equals 3 cubed. Once they're the same bases, that means 2x must equal 3, and x equals 3 halves. Divide by 2. 4 is 2 times 2. 8, we already said, is 2 times 2 times 2. So on the left-hand side, I'll have 2 squared raised to the x minus 2. On the right-hand side, I have 2 cubed raised to the x power. 2 squared is 4, 2 cubed is 8, so then I just rewrote them like that. So now, same basis, so powers raised to powers, they multiply. This is 2 to the 2x minus 2, in parentheses, equals 2 to the 3x. Now that I have same bases and they're equal, I can set those equal to each other. 2x minus 4 equals 3x, and you might be saying, where'd that 4 come from? 2 times x and 2 times 2. I just did distributive property. Add 4 to both, or sorry, subtract 2x from both sides. Negative 4 equals x to solve for x. We just did that. As a result of a nuclear accident, radioactive material was carried through the atmosphere. One immediate concern was the impact of the debris had on the milk supply. That is because if it's carried through the atmosphere, it's going to get to your cows. Cows are going to inhale it. It has an effect on milk supply. The percent Y of radioactive material in raw milk after T days is estimated by this function. Estimate the expected percent of radioactive material in the milk after 30 days. For this case, it's looking at the formula and saying, all right, well, what's going on here? And what are my variables? Y is the percent of radioactive material. T is the, is it number of days? Must be. So if they give you 30 days, then it's a matter of looking at that equation and trying not to get freaked out saying, don't worry, y equals 100 times 2.7 to the negative 0.01 times 30, number of days. And then it's doing order of operations. Negative 0.01 times 30 is negative 0.3. Then you do exponents, 2.7 to the negative 0.3. And then times 100. I'm assuming you're all doing that with your calculators right now. That's what I got on my calculator. Did anybody get the same number?
Yeah.
Good. And it's a percent, so I'm going to write percent. That's what the times 100 means. So after 30 days, T days, after 30 days, it's estimated that 74.3% radioactive material will be still in the milk. So probably not a good thing to have radioactivity in your milk. Probably not. So those are the check your understanding problems that you're working on. This is all in the modules. All right. So then